there. I hope that you've been doing well. This is a video to be paired with Workshop 10, Regression with Categorical Predictors. This tutorial will walk you through it. Please do it yourself as well. And I hope that it helps you as you do more regressions. Okay, so first, the main premise of this video is that regression works differently, just a little differently, if you use continuous numeric predictors versus categorical predictors. That means if you're trying to model an outcome, if your explanatory variable is numeric, it works just like we've used before, just like we've done before. But if it's a categorical variable or a binary variable, it's going to be a little different. And this is the same if they're combined. Okay, so one place where we see a lot of categorical variables is in the wine reviews data set. So let's check out an example using that. For example, using this line of code, we can grab 1,000 wine reviews from this data set of 130,000 different reviews of different wines. Okay, and we're going to grab just 1,000 of them because that's a lot of data and we only want a few of them. It's going to take a moment. Okay, and there, it's loaded. So if we view this, selecting just the vectors point, price, and country, we will see the first few rows in this data set. And we see that the points, the rating of the wine, is here. So this was 95 on a scale from 0 to 100. The price, this is its price in US dollars. This is the country where the wine is from. So you can kind of see where this is going. Do wines that are more expensive get rated better? Or do wines that are from certain countries get rated better? We can run this model quite straightforwardly, and in fact, we just did. You can see what we've done here. Okay? And holy moly, there are a lot of beta coefficients in this model. Specifically, there's a beta coefficient for every level of the categorical variable. Isn't that cool? So you'll see, first we've got our alpha. This is the expected rating independent of everything else. So about 85 points you're going to get off the bat. This is the beta coefficient for price. So as the price goes up by $1, you expect the review to go up by about 0.03 points. And this is the beta coefficient if the country is Australia, if the wine was made in Australia. This tells us that we expect the outcome, the wine review from 0 to 100, to go up by 1.5 points if it's from Australia. But if it's from Austria, we expect it to go up by 3.45 points. And if it's from Bulgaria, 3.07 points, right? And we have this for all of the different categories. It's kind of neat, right? Couple quick points. You need to have enough rows in your data set representing different categories for this to work. I mean, it's really hard to make a prediction off of just like three, like if you just had 3 wine reviews that were from Australia. That would be hard to use. So we need lots of data. So this is why we like large sample sizes. But this is pretty powerful. Quick thing. It would be hard to know this, but we haven't actually seen all of the countries here. Whenever you use categorical data, one country or one category becomes the baseline. After all, how do you even compare this stuff, right? The effect of one category relative to having no categories, that's not really an option, right? We can't really compare what the effect of being from Australia is compared to the effect of being from nowhere. That's not a thing, right? You have to be from somewhere theoretically. So this model actually what it does is it takes one of those categories, it takes the one that comes first alphabetically, and makes that the intercept. So, if I remember this correctly, Argentina is actually the baseline country. And that's why we don't see Argentina on this list, even though it's one of the categories. So, Argentina has become the baseline by default because it comes first in the alphabet among this list of countries. And that means we can actually interpret the intercept in a very interesting way. This means the intercept here says how many, in this specific instance, because we're using categorical predictors, the intercept now means how much, how highly would you be rated if you were from Argentina? And then the country Australia means, as we discussed, how much more highly would you be rated if you were from Australia? I'm just going to say that one more time to make sure I got that right. The intercept for categorical data means independent of everything else, Argentinian wines get rated at about 85 points on a scale from 0 to 100. But if they're from Australia, they get rated 1.5 points higher than Argentinian wines. If they're from Austria, they get rated 3.45 points higher than Argentinian wines. And if they're from Chile, they get rated 0.5 points lower than if they were from Argentina. Okay? And we can do this in a cool way. We can project what we can say that actually, if you were from Australia, we know that then Australian wines tend to have, while the effect is like 1.5 points, they tend to have, independent of everything else, this score plus the effect of Australia. So an Australian wine tends to have 85, like 87.25 points on a scale from 0 to 1.5. And what we just did was we added the intercept and the effect for Australia together. Okay? It's kind of nifty, right? So you just remember that when you do categorical data analysis, the intercept becomes the baseline category. Okay? So what if we don't want Argentina to be the baseline? What if we actually want to know the effect of being Argentina? So we'd want a beta coefficient for it. Currently, we just get the alpha coefficient for Argentina. We just get the intercept. So we'd have to choose a different category to be our baseline category. It is surprisingly easy. Let's see what we do here. Okay, so we have our wine data frame. We can mutate the wine data frame and say, hey, make our vector country equal to everything that comes after this. And what comes after it is, we're going to say country, turn country into a factor, and that's done by pipelining to the factor. And that's the same thing that R does. Normally, it automatically does that when you run a regression on a categorical variable. But we need to say, okay, once you've made it a factor, I don't want Argentina to be the baseline anymore. I want Australia to be the baseline now. We do that by saying relevel where the reference, the baseline value, is Australia. And we do all that, we save it back into wine so that wine is permanently changed. And you can actually look at our wine data set, and this is all of the different categories on here. Let's see. If we go to country right here, we can actually see that this has been changed from the CHR to FCT, meaning factor. Kind of indicative of what we did to it. We gave it levels. We gave it levels in a specific order. Okay, so let's rerun this model. Let's find out what the effect of being Argentinian has on wine. Okay, and here we go. You'll notice that Australia is no longer given a beta coefficient here. That's because Australia is represented by the intercept. So if you're from Australia, you get 87 points just to start, independent of everything else. And if your wine is just slightly is more expensive by $1, you get 0.03 increase. But if you're from Argentina, your wine goes down. The review of your wine goes down by 1.5 points. If you're from Austria, it goes up by 1.95 points. And say, if you were from Argentina, you'll notice that we could literally take 87.26 and subtract 1.50, and that would be what you'd get independent of everything else being from Argentina. Fun fact, that's also the intercept that we had before. Okay, kind of interesting, right? So this would be really helpful if you wanted to, for instance, find the effect of being male versus female, of being from one political party versus another political party. But let's say that we were doing a study and we really cared what's the effect of being Republican on something. We didn't really care what the effect of being Democrat was. We cared what the effect of being Republican was. Then it's going to be really important to use that relevel ref equals Republican function to figure that out. Okay. All right. So cool. We've done regression with categorical predictors. Yay, that was very easy. How might this change our regression assumptions? Most of them it doesn't, but there are a couple things that matter. First, let's take a peek here at the VIF, our variance inflation factor scores, which are our primary means of figuring out multicollinearity, figuring out if our predictors are related. Holy what? Yeah, so you'll see now, and let me just redo that one time so that you can see it better. We just ran this function, and the results do not look the same. They're outputted in a totally different format. Usually we expect just a line going out that says price 1.3, something else 3.5, blah, 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 right? But now we've got an entire matrix. Here's what's going on. This first column, GVIF, that is the result you'd normally get. Here's the problem. GVIF tends to be super inflated for categories. It's just bad at it. It's not the appropriate measure for it. Instead, you can create this cool measure called GVIF to the 1/2 times the degrees of freedom power. They need to work on the name. It's not very good. We can just generally call it the generalized variance inflation factor. And what's nice about it is it says, okay, we're going to control for the number of categories. There are 18 different categories in this variable. Great. We're going to factor that in. The problem is once we do that, this measure is going to be, it's not going to be on the same scale as when we first learned VIF. And the whole world is used to understanding VIF on that scale. So to get back to that scale, it's really, really quick. Here's what you do. You run this function, and you read the third column. That is your VIF score. Pretty straightforward, right? So with normal categorical data, with normal numeric data, you don't have to worry about this. You can just run VIF and trust the results that it gives you. But when you use categories in your predictions, you can instead go right here. You can square it and look at the third column, and that's your VIF. Okay? Pretty great. It may affect you for your final projects if you choose to do like the wine reviews data set or something. And if you choose to do something that doesn't have categorical data, then it won't affect you. So don't worry. Okay, so we've talked about the wine data set. It might be helpful to think a little bit more about another example. Here's one. I made a data set of Japanese municipalities from 1980 to 2020. And if you run this code, which has a bunch of things in it, it's going to do a few things. It's going to say, hey, please grab all of those towns over those years that were in the disaster zone. Remember this from our earlier lab, that were in Fukushima, Miyagi, or Iwate prefectures, and grab each of these variables. Ooh, lots of good things. So we've got things like population and age and gender, whether they were hit by the tsunami, whether they're in the Fukushima exclusion zone. Those variables should sound familiar. We've got the year, we've got the prefecture, the income per capita. Yeah, as you can see here, I've kind of got something set up. We can try and figure out, did getting hit by the tsunami affect the general wealth of a community over time? Nifty, right? So if we run this, boom. It's going to take a moment because it's loading. Okay, and we've got 882 town observations over time. And we can understand that a little bit better if we run the head function, which gives us the first 6 rows. Okay. And it's kind of interesting. What we're actually seeing here, and I'm going to edit this real quick so we can see it a little better. We are seeing the following trend. We have data on the same city for many, many years and different income per capitas for each year. It's kind of like a measure of wealth. Okay, great. How does this relate to categorical variables? Well, if you have data on lots of towns over time, you could test, did getting a treatment like a tsunami, bad treatment, does getting a treatment lead to a change in an outcome like income per capita? Whereas before we did a straightforward t-test where it was like, overall, if you got the tsunami, did you get more solar plants? We could do it in a more nuanced way. We could say like, okay, over time, if you got the treatment, did you have a change in income per capita? So let's see what that would look like. This is, by the way, a straightforward example of how you could use the Japan dataset. There are variables of several treatments, like getting hit by the Kobe earthquake, getting hit by the 2011 quake. There's, I think, whether they host a nuclear power plant. There's lots of stuff to do with this. So if you are interested in using this for your final project, please be in touch and feel free to continue with this example. Okay, so first we're going to turn our treatments into vectors, into factors, where we say this is the reference category that we care about. Okay, so we say make tsunami a factor where the reference, the intercept, is going to refer to if the tsunami didn't hit you. That's helpful because that way we can find out what the beta coefficient is if the tsunami did hit you. That's kind of what we care about in this case. We care about if you were hit, not if you weren't, right? If we cared about the reverse, we would code this as 1, right? Because the tsunami column, let's take a peek at what the tsunami column looks like. Tsunami. Yeah, the tsunami is all zeros and ones. Yeah, so we've got all zeros there. So zeros means they weren't hit, 1 means they were hit. Great. So we want to say our baseline category is 0. Our baseline category for exclusion zone is 0. That means we assume by default that they weren't in the exclusion zone, and we care if they were. We want to see that effect. We also are going to make our year into a factor that is going to treat year as a categorical variable. So we could see what the effect of 1 year versus another is. We're going to turn prefecture into a factor where Iwate prefecture is going to be our baseline. You see how we're making some neat decisions about how we're going to treat our data, and you can too. Okay, great. So we can run a regression model right here where we're going to test the effect of 2 treatments at once. This is kind of like level 2 for experiments, you know. Okay, so we're going to run our model. We created something called M1, that's our new model. And we're going to visualize the variation in residuals. Let's check it out. All right, let's see what we got. Remember the other day when I was talking about model assumptions, how one of them was independence of observations? If these were all this, if these observations were independent, we would expect this dotted line to be just like the same throughout. Right now it's broken up because we've got categories, right? But we would expect that this would be a continuous dotted line about the same height as this one. But that is not happening, right? We're seeing kind of a fan shape happening, okay? Fan, bad news. Why? What we're technically seeing is that the variance in residuals is different for different outcomes. That means that our residuals are not normal. That means that we have non-constant variance. This is what it means. This is what that test means. But the thing is, usually there are tricks to making it work. So just because you find that you have non-constant variance doesn't mean that the show's over. You can work this out further. By the way, how did we make this plot? We created a data frame of our model fitted values, our y predicted, and of our residuals, so the observed minus the predicted values. And then we just visualize them on a scatter plot. It's kind of cool, right? Okay, so let's take a peek at this. What if we controlled for year? That might help break this up a bit. That might help deal with one of the ways that our data is interdependent. We could control for time, and therefore take care of the fact that our observations are involve the same cities over time. So they'd be less interdependent if we controlled for it. Okay, so we run M2, where we've added year at the end, and that's new. And if we run this again, okay, it's breaking up a little bit, and it's even looking a little better already. We still see some variation, like this is not the same, but at least their heights are getting more similar. Well, maybe some towns had similar income per capita just because they were in the same prefecture. So if we added prefecture in, maybe that would help too. Let's try it out. See what happens. Oh, wow. Well, it doesn't change very much. It does seem to have gotten better, so that's good. And then what if we added some demographic controls? Maybe that would help it would help resolve some of the issues. It would tell us why some towns are similar to each other, right? So it would kind of break that up. Let's try that out. And let's visualize it. Very different all of a sudden. Interesting, right? If we truly had constant variance, this would just be like a cloud of points, and we wouldn't really see any particular trend. Here we can see that, yeah, all these dots, these are probably the same town. So they kind of cluster together still. So that's still like some interdependence, but we've managed to take care of a lot of it, right? Remember how just before with M1, with our first model that had no controls for time or controls for prefecture or any of that, or demographics, it looked like this, where we had a big fan shape going on, really non-constant variance. But by the time that we've added all these demographic controls, it looks like this. It's much better. Here's the problem. The non-constant variance test that I taught earlier, NCV test, is unforgiving. If we run this, it's giving us a p-value that is very, very tiny. So it's saying there is definitely non-constant variance happening here. And another way of saying that is there is definitely heteroscedasticity happening here. They mean the same thing. Cases are definitely interdependent. At this point, it's kind of hard to say what to do. If you find this in your final project, first of all, I am A-okay with that. Don't worry about it. But if you're working with data that has multiple observations for the same place over time, like the Saitama greenhouse gas data, or the Japanese municipality data, or the, I think the vote view data has this too. Be sure to control for year. That's going to make things a lot better. It's going to make your estimates a lot better. The reality is we're all making a good faith attempt at trying to model this data the best that we can. OLS, or regression, as we've been calling it, is really useful, and it's very flexible. And it tends to be pretty good at working with this kind of data, with data with non-constant variance. It tends to be pretty good at working with interdependent data, even though it violates one of their assumptions. This being said, if you are going to sit down with a policymaker or with a CEO or a nonprofit and convince them, yeah, you should definitely do this, you should definitely adopt this policy, you'd better be pretty sure that you've got your model assumptions checked, right? So in that sort of situation, I'd advise you go talk to me, you talk to a statistician, and ask, hey, what model could I use other than a regression model that would deal with heteroscedasticity, that would deal with non-constant variance? Okay, so that's a long way of saying you can make excellent models that still struggle on some kinds of assumptions. And our job is to try and make the best models that we can of our data, while keeping an open mind that we might have errors. Just be careful not to assume that your model is perfect. Always have a little bit of skepticism, and I think that will take you far. So, okay. With that in mind, I hope that this has been helpful. Today we learned how do you use categories as predictors, and we applied it to the wine reviews dataset. We also tested using categorical predictors for kind of a super t-test, right, where we conducted a little experiment to see did getting hit by the tsunami or being in the Fukushima exclusion zone, did that affect your income per capita? By the way, we never actually checked the results. Let's see. We were so focused on the model assumptions that we didn't look at that. Well, let's see what we get. We explained a lot of variation in the data, probably because we controlled for prefecture and year. And we got a whole bunch of estimates. It's pretty cool. And so we see that in general, getting hit by the tsunami actually seemed to boost your income per capita a little bit, as did the exclusion zone, which is very confusing, right? This is because a lot of those towns got hit by more, received a lot of aid, and so their income per capita went up. Okay, if you have any more questions, please shoot me an email. Happy to Skype or talk about it, and hope you have a great day.